So, we start a new module, microwave networks and scattering matrix. So, in this we will cover the following contents: impedance and equivalent voltages and currents, N-port microwave network, impedance, admittance and scattering matrix representations, and reciprocal and lossless networks. Also, we will discuss about the transmission matrix. So, let us start our discussion with impedance and equivalent voltages and currents. What happens at microwave frequencies? Measurement of voltage or current is not practical unless a clearly defined terminal pair is available. So, this terminal pair we call it a port, and such terminal pair may exist for TEM type lines, that means transverse electromagnetic wave propagation only, but does not exist in a strict sense for non-TEM lines. And therefore, the voltage and current as a measure of level of electrical excitation of a circuit does not play primary role at microwave frequencies. However, we can introduce the concept of equivalent voltages, equivalent currents and impedances, and which is helpful in extending the circuit theory concepts to microwave network. For transmission lines supporting TEM waves, the voltage and current are uniquely related to the transverse electric and magnetic field respectively. And let us illustrate this by an example. So, we show a section of a coaxial transmission line. So, we have a coaxial transmission line with inner radius A and outer radius B. Now, these radial lines, these are the electric field and the magnetic field lines are shown by this circle. Now, for such line we can find out the electric field to be V naught by log of B by A into e to the power minus j k z by rho. So, this electric field is directed along rho, and here k naught is omega root mu naught epsilon naught. Voltage V naught is the potential difference between the inner and the outer conductor. So, for the same transmission line we can associate a voltage wave with the electric field, and this is given by V is equal to V naught e to the power minus j k naught z. Similarly, for this type of coaxial conductor, the magnetic field is given by H is equal to y naught V naught divided by log of B by A e to the power minus j k z by rho A phi. So, the magnetic field, the current associated with the magnetic field can be written as I is equal to I naught e to the power minus j k naught z. Please note that y naught is the characteristic admittance and I naught is given by y V naught 2 pi log of B by A. So, once we define these equivalent voltages and currents and relate them to the electric and magnetic fields, we can calculate also the power that is going through such coaxial transmission line, and power is given by integration of the Poynting vector over the cross section of the transmission line, and once it is evaluated we get pi y naught v naught square log of b by a. If we find the power from the current and voltage wave, that means I and V, which we have just defined, then half R e V I complex conjugate, this also gives the same quantity pi y naught v naught square by log b by a. So, we can see that whatever power we calculate using these field equations, if we consider the equivalent voltage or current equation, the same power flow is evaluated on the coaxial line. So, these voltages and currents can essentially represent in a equivalent manner transverse electric and magnetic fields, and also we find that Z naught is equal to V naught by I naught, which is the characteristic impedance. So, when we have a TEM transmission line and we have a clearly defined pair of terminals, it is relatively easy to introduce the equivalent voltage and currents, because this voltage and currents, these are well defined. When we go to a single conductor system like waveguide, where propagation mode is non-TEM, we face difficulty in defining such voltages and currents. So, this we illustrate. Let us consider the dominant T10 mode of a rectangular waveguide and its electrical field distribution as we show in the figure. Now, here if you consider, if we want to calculate the voltage, what we will do? We will integrate this electric field from y equal to 0 to y equal to b, that means along y, and once we substitute the expression for the Ui and integrate, we find that the same integration now has a term sin pi x by a. So, for x is equal to 0, the voltage we will evaluate to 0, whereas x is equal to a, we will get again the voltage to be 0, we will have a peak voltage at the middle. So, what we find that if we consider this type of single conductor transmission line like waveguide, we cannot uniquely define the voltage, and the voltage will vary depending upon where this voltage is evaluated. So, voltage depends on the position x for this type of waveguide. Now, next is how we can introduce actually the equivalent voltages and currents in this type of waveguiding systems. So, we note the following properties of the propagating modes in a waveguide. The power transmitted is given by integral involving the transverse electric and magnetic fields only. So, when it comes to computation of power of the inside a waveguide mode, it is essentially involves the transverse electric and magnetic fields. In a loss free waveguide supporting several propagating modes, power transmitted is the sum of individual modes. Then transverse field vary with distance along the guide according to a propagation factor e to the power plus minus j beta z, and the transverse magnetic field is related to the transverse electric field as ZW, which is the waveguide impedance, and H is the transverse magnetic field Az cross E bar. So, these properties of the waveguide propagation will make use of in defining equivalent voltages and currents. So, these properties essentially suggest that equivalent and voltage and current can be introduce proportional to the transverse electric and magnetic field. So, whenever we define equivalent voltage and current, we try to relate those voltage and current to the transverse electric and magnetic field components. Now, equivalent voltage, current and impedance for waveguides can be defined in different ways, as these quantities are not unique for non-TEM lines. However, if we use the following consideration, then some uniformity can be maintained. The voltage and current are defined only for particular waveguide mode. So, every waveguide mode is essentially represented similar to a transmission line. These are defined so that voltage is proportional to the transverse electric field and current is proportional to the transverse magnetic field. Equivalent voltages and currents should be defined in such a way their product gives the power flow of the waveguide mode. So, as we are defining these voltages and currents, equivalent voltages and currents for individual modes, now they are to be introduced in such a manner the voltage and current, when they are taken into computation of power, they will actually correspond to the power flow of that particular waveguide mode. The ratio of voltage to current for a single travelling wave should be equal to the characteristic impedance of the line. Now, impedance may be chosen arbitrarily, but usually selected as equal to the wave impedance of the line. Sometimes Z0 is set equal to ZW, or else it is normalized to unity. So, the equivalent voltage and current waves can be written as Vz is equal to V plus e to the power minus j beta z plus V minus e to the power j beta z, and Iz can be written as I plus e to the power minus j beta z minus I minus e to the power j beta z. And we define the characteristic impedance Z0 to be equal to V plus by I plus or V minus by I minus, and as we have said, Z0 can be made equal to ZW, the wave impedance of the waveguide mode, or it is normalized to unity. Now, let us consider an N-port microwave network. So, this is the schematic of an N-port microwave network. The port may be any type of transmission line or transmission line equivalent of a single propagating mode. So, we can see that if it is a TEM transmission line, we can define this port directly, or if it is a waveguide type port, then we have a transmission line equivalent of a single propagating mode. If the physical port of a network is a waveguide supporting more than one propagating mode, so in many cases it might happen that the single physical port, it is supporting more than one propagating mode. In such cases, the modes can be accounted by considering additional electrical ports. So, we can increase the number of ports accordingly. Now, once we have the equivalent voltages and currents defined, at the nth port we define a terminal plane Tn. For example, this is the T1 terminal plane, and also the equivalent voltage and currents for both incident and reflected waves. Now, what we do, this terminal plane essentially serves as the phase reference for these waves. So, if we shift the terminal plane, there will be a change of phase, and we can define these terminal planes for each of the ports as shown. and we have this V 1 plus I 1 plus, these are the waves that is going into the network through this port, and V 1 minus and minus I 1 minus, these are the waves which are coming out of the port. And we have already mentioned that these terminal planes are important for providing phase reference for voltage and current phasors. So, this is how we have defined an N port microwave network. Let us now see some practical circuits where this type of multi-port microwave network actually occur. For example, here we show a 2-port network which is essentially a filter, and these two are the ports. Similarly, we can consider a case of a power divider. Here the input signal incident on this port is split between these two ports, so that it divides the power, and it is a 3-port device. Similarly, we consider a waveguide version of a magic T, which is a 4-port device, and if we consider the microstrip or planar version, this is called a hybrid coupler. So, you can see it also has 4 ports. So, you can see that physical microwave circuits or network will have one or more number of ports, and how we define the voltages and currents in these ports, these are through, if they are TM lines we can directly define, or if they are non TM lines we can always have an equivalent voltage which is related to the transverse electric field, and an equivalent current which is related to the transverse magnetic field components. So, we have at the nth terminal plane V n is equal to V n plus V n minus. So, this is essentially obtained by putting z is equal to 0, and I n becomes equal to I n plus minus I n minus, and the impedance matrix Z of a microwave network relates these voltages and currents. So, for a n port network we can define V 1, V 2, V n, these are the voltages at ports 1, 2 and n, and I 1, I 2, I n, these are the currents at ports 1, 2 and up to n, and these two vectors, they are related by a matrix which is called the impedance matrix Z, Z11, Z12, Z1n, Z21, like that Zij are the entries for this matrix. So, we have in the compact form we can write V is equal to Zi, where V is a vector, Z is a matrix and I is the vector. In the same manner, we can define another matrix which is called the admittance matrix Y. Here I 1, I 2, I n, they are defined as a matrix Y multiplied by the vector voltage vector V. And we can see that Z and Y, they are inverse of each other. Now, how we define these parameters? For example, if we consider Zii like Z11, the diagonal elements, Z11, Z22, Z33. So, it is Vi by Ii, and when Ik is equal to 0, k is not equal to I. So, if I go to the definition, for example, Z11 will be V1 by I1 when I2, I3 up to In they are all 0. And therefore, ZII is the input impedance seen at the port I when all other ports are kept open circuited. Similarly, Zij is Vi by Ij and all Ik equal to 0 for k not equal to j, and this will give the transfer impedance between port I and j when all other ports are open circuited. So, these Z parameters, these are open circuit parameters. That means, if you are to measure Z11, you will have to keep all other ports other than port 1 open circuited. In the same manner, we can find Yij, and you can determine by driving port j with voltage Vj and short circuiting all other ports and measuring the short circuit current at port I. Now, for a reciprocal network, the impedance and admittance matrix, they are symmetric. That means, we can write Z is equal to Z transpose and Y equal to Y transpose. By reciprocal network, we mean that it will not contain any active devices, ferrites or plasmas, and the if a network contains any of these elements, it cannot be modeled as a reciprocal network. So, we have seen that for a reciprocal network, the Z and Y matrices are symmetric. Let us now consider a lossless network. So, if a network is lossless, then what we can write? We can write that the real part of the average power to be equal to 0. Now, how we can calculate this average power? We can actually find the product of V and I conjugate at each port, which in the matrix form we can write V t transpose of V into I complex conjugate. And then once we substitute V is equal to Z I, and then using the property of transpose, we can write I transpose, it should be Z transpose, but since Z is symmetric, therefore, we can write I transpose Z I complex conjugate. Now, this can be expanded as shown. We can have I transpose as a row vector, then the Z matrix and I conjugate as the column vector. Now, once we find out this product, matrix product, we can put the average power expression in this form, and starting from this form, if we now find out the product of this row with this column, we can write the expression for average power in the form shown, and we can see that each term within this bracket, first bracket, it is one summation, and then it has been multiplied by I 1, I 2. So, we can write P average as a summation of m to n, as a summation of m is equal to 1 to n equal to 1 to n, I m, z m n, I n conjugate. Since ions are independent, let us set all port currents to be 0 except for the nth port. Therefore, this essentially, when only one port is excited, this double summation term results into this term I m z n n I n star, and this can be written as mod of I n square real part of z n n is equal to 0, since we have I n not equal to 0. So, we find that real part of z n n is equal to 0. That means, the diagonal elements, the real part of the diagonal elements of the Z matrix, they are 0. Let us now consider the off diagonal elements, and to calculate this, let us now consider that all port currents except I m and I n are 0. Then in the same manner, we can write I m z m n I n conjugate plus I n z n m I m conjugate, real part of this is equal to 0. Now, this can be written as real part of I m I n conjugate plus I n I m conjugate z m n is equal to 0. Since we have the matrix which is symmetric, now this quantity I m I n conjugate plus I n I m conjugate, this quantity is always real. If you expand I m and I n in terms of real and imaginary part and find out the expression, this will a real quantity, and in general it will be non-zero. So, we can say that real part of z m n is equal to 0, and therefore, real part of z m n is 0 for any m and n. Therefore, if you consider a lossless network, the elements of Z must be purely imaginary. And in the same manner, elements of Y can also be shown to be imaginary. So, this property that the elements of a lossless reciprocal Z or Y matrix, they are purely imaginary. We will see some examples later on. Now, let us see some Z matrices for different types of network. For example, if you take this network, here we find that it is neither lossless nor reciprocal, because it has entries which are real and it is not symmetric. So, this Z matrix is neither lossless nor reciprocal. Similarly, if you take this matrix, it is lossless, but not reciprocal, because we have all the elements to be imaginary. This gives an example of a Z matrix which is reciprocal, but not lossless, and this is the case where the Z matrix is both reciprocal and lossless. We discussed about equivalent voltages and currents. So, let us consider an example to illustrate how we can find those equivalent voltages and currents for a propagating mode in a waveguide. So, to illustrate this, we consider TE10 mode propagation in a rectangular waveguide. And for a TE10 mode in a rectangular waveguide, when the waves travelling in both plus z and minus z directions are present, the transverse field components we can write in this form: a plus sin pi x by a, this is the variation of the field component u I, e to the power minus j beta z, and this is the wave travelling in the plus z direction, and a minus sin pi x by a, e to the power j beta z, this gives the wave travelling in the minus z direction. So, we can put it in this form, and we know that the transverse magnetic and electric field components, they are related by this equation. H transverse is Az cross E transverse by Zw, where Zw is the waveguide impedance, and this relation holds when we consider the wave is propagating along Z. So, from this relation, once we have written Ui, we can write the expression for Hx to be equal to minus 1 by Zte a plus e to the power minus j beta z plus a minus e to the power j beta z sin pi x by a. So, the power for the incident wave, let us denote it by P plus, and from this Ui and Hx component we can find this power to half 0 to a 0 to b. If you integrate this a plus square by Zt sin square pi x by a, that means over the cross section of the waveguide, then this will give us the power in the incident wave, and once you evaluate this integral, we get P plus to be equal to AB divided by 4 Zte a plus magnitude square. Now, we can also write equivalent voltages and currents. So, Vz can be written as V plus e to the power minus j beta z plus V minus e to the power j beta z, and Iz can be written as I plus e to the power minus j beta z minus I minus e to the power j beta z. And this Iz can also be written in terms of the voltages V plus and V minus. So, from this expression, if we consider the incident power P plus, then it is given by half V plus I plus conjugate. And now, let us consider two constants C 1 and C 2, which relates this V plus with A plus and V minus with A minus, I plus with A plus and I minus with A minus. A plus A minus, these are the, as we have seen, these are the amplitude of the transverse field components. Now, we have two expressions for P plus, one evaluated from the fields, another evaluated from the voltage and current, and if we equate these two, then we can write A B by 4 Z T A plus mod square is equal to half V plus I plus conjugate. Now, here what we can now do, we can replace V plus and I plus in terms of C 1 A plus and C 2 A plus. So, if we do that, then this becomes half A plus modulus square C 1 C 2 conjugate. And let us, as we said during our discussion of equivalent voltages and currents, Z naught can be either said to be equal to Z T or it can be normalized to unity. Let us set Z naught equal to Z T. In that case, we have V plus divided by I plus is equal to C 1 by C 2 and equal to Z T. So, if we consider C 1 C 2 to be real from the previous two equations, that means A B by 4 Z T is equal to half C 1 C 2 conjugate and C 1 by C 2 equal to Z T. From these two we can find out C 1 to be equal to under root A B by 2 and C 2 will be 1 by Z T under root A B by 2. So, with C 1 C 2 known, what we can do? We can find V plus, I plus, V minus and I minus in terms of amplitude A plus and A minus. Let us now consider another example. Let us consider a rectangular waveguide of dimensions A is equal to 2.5 centimeter and B is equal to 1.25 centimeter. And let the waveguide be filled with air for Z less than 0 and a dielectric material with epsilon r is equal to 2.25 for Z greater than 0. So, this is shown here. So, in this part it is air field, in this part of the waveguide it is dielectric field. Now, let us apply the concept of equivalent transmission line model to compute the reflection coefficient for the TE 10 field incident on the interface from Z less than 0. So, that means what we are assuming, a wave is incident from this side, from the waveguide, air field waveguide, and then part of this incident wave will get reflected because there will be a change in impedance here and partly it will get transmitted. So, let us try to find out the reflection coefficient for this system, assuming that the propagating mode is TE10 and the frequency of operation is 7.5 gigahertz. Now, for the given guide dimensions, one may verify that at 7.5 gigahertz only TE10 mode propagates in both the portions of the waveguide, and that can be verified by calculating the cutoff frequencies for different modes in both the waveguide. So, we will find that at 7.5 gigahertz only TE10 mode will get excited and higher order modes will have cutoff frequencies higher than 7.5 gigahertz in both the guides. Now, the cutoff wavelength for TE10 mode in a rectangular waveguide, it is given by 2a, and therefore, we can find out the cutoff wave number k c is 2 pi by lambda c, which becomes equal to pi by a, and for the given dimension a, it can be calculated to be 125.66 per meter. Similarly, k naught is 2 pi f root mu naught epsilon naught, and that can be calculated for the given frequency 7.5 gigahertz to be 157.1 per meter. So, once we know k naught, we can find out beta a, the propagation constant in the air filled waveguide, and that will be given by k naught square minus pi by a whole square, and if you substitute the values, you will get the value of beta a to be 94.3. Similarly, when beta d inside the dielectric waveguide is calculated, there it is instead of k naught, it is k square, and therefore, it will be epsilon r into k naught square, and it comes out to be 199.35 per meter. Now, the wave impedance Z naught A for the TE10 mode in the air part of the waveguide, it can be found out to be k naught, eta naught is the intrinsic impedance of the free space divided by beta a, and once these values are substituted, eta naught is 377 ohm. So, it comes out to be 628.1 ohm. Similarly, Z naught D inside the dielectric portion of the guide can be found out as k eta by beta d. K we can write root epsilon r k naught, and eta can be written as mu naught by epsilon r epsilon naught. So, this root epsilon r cancels and Z naught d is given by k naught eta naught by beta d. So, once again, once we substitute these values, we get this to be equal to 297.1 ohm. We know that the reflection coefficient gamma will be Z naught d minus Z naught a divided by Z naught d plus Z naught a, and once we substitute the values for Z naught a and Z naught d, the reflection coefficient comes out to be minus 0.8. 0.36. So, this is how we can apply the concept of equivalent transmission line voltages and currents for a single propagating mode, and we can calculate the reflection coefficient at the interface of this air and dielectric.